Hello, today we will speak about the trainer class that is designed to manage the training and validation processes for our recommendation system. This class centralizes the core logic required to train the model on a dataset, calculates the error during training, and evaluates performance on a separate validation set. Our training class will have two main methods, train and validate. The train method updates the model's parameters to minimize the loss on the training data, and the validate method, which evaluates the model on the validation data. The library that we are going to use is PyTorch, or more specifically, Optim and NN. Optim includes optimizers for updating model parameters, and NN provides essential building blocks for creating neural networks, including layers, loss functions, and other computations to define and train models. Our class will also automatically detect if a GPU is available, and if so, it utilizes for faster computation, otherwise it defaults to the CPU. Through these tools and methods, the trainer class efficiently manages the process of training the recommendation model for our recommendation system and tracking its performance, making it an essential component for model improvement and evaluation. First, we need to define our class trainer and its constructor. In that constructor, we are going to use a few parameters: model, training, loader, val loader, LR, and num epochs. The model variable represents the recommendation model that will be trained. It contains the neural network's architecture and parameters which will be updated during training. The train loader is a data loader object that loads the training data in batches. The model will use these batches to learn from and update its parameters based on the training samples. Val loader is another data loader object, but for the validation set. It's used to evaluate the model's performance on unseen data after each epoch, helping gauge if the model is generalizing well. LR, the learning rate, is a hyperparameter that controls the speed of the model's learning. Setting the right learning rate is crucial because a high rate may lead to overshooting the optimal solution, while a low rate can result in slow learning. Num epochs equal to 10. That defines how many times the model will go through the entire training dataset. Next, we are using ADAM Optimizer Adaptive Moment Estimation. It is widely used for deep learning because it adapts the learning rate for each parameter, often resulting in the faster convergence. The optimizer updates the model's parameters to minimize the loss function. Loss function. MSE loss. Mean squared error loss function. This is a common choice for regression task where the goal is to minimize the difference between predicted and actual values. Device settings, CPU or GPU. This line checks if GPU is available. If it is, GPU is used, otherwise defaults to CPU. Next line sends the model to the selected device, GPU or CPU. This is important because it ensures that all computations are performed on the same device, which is necessary for efficient data processing and avoiding errors in PyTorch. Next is our training method that is designed to loop through the training data for a specified number of epochs, where each epoch is one complete pass of a training dataset. The purpose of each epoch is to progressively adjust the model's parameters to minimize the difference between the model's predictions and the actual ratings. The line self-model train sets the model to training mode. That ensures the model is ready to learn and adjust its weights. In each epoch, the model processes data in batches. For each batch, user item and ratings are loaded from self-train loader. The user and item are converted to the correct data type and transferred to the appropriate device, CPU or GPU. This step is required to work with embedding layers in the model. The ratings are also converted to a float type and moved to the proper device, and after that we reset the gradients. The loss backwards line computes the gradients of the loss respect to each of the model's parameters. After calculating the gradients, self-optimizer step updates the model's weights using these gradients. This optimization step is critical as it allows the model to learn by minimizing the error over time. After each epoch, the batch loss is added to total loss, which tracks the cumulative error for that epoch. At the end of each epoch, the average training loss for the epoch is printed, providing feedback on how well the model is learned over time. Monitoring the loss at each epoch is essential, as it shows whether the model's error is decreasing, which indicates successful learning. And our second important method, validate. The line-safe model eval puts the model in evaluation mode. That ensures consistent and accurate validation results. The next line, or torch no grad, blocks turns off gradient calculation. This saves memory and speeds up the process since gradients are only needed for training. The method loops over each batch in val loader, just like in training. The user item and rating again are converted to the correct format and moved to the proper device, GPU or CPU. The line prediction is used to predict ratings for the batch. Then loss calculates the difference between these predictions and actual ratings. The batch loss is added to val loss to keep a running total of the error across all batches in the validation set. After looping through all validation batches, the average validation loss is calculated and printed. This average helps evaluate model's performance on unseen data without updating the model's weight.